Greetings, technical artists. Welcome back to the second video in our Introduction to Machine Learning. And we covered a lot of stuff and we spent a lot of time going over that last machine learning code that I gave you here. You already said, my God, this thing is huge. Okay, don't freak out. There is a lot of stuff in there, but I'm going to explain what most of this stuff is now. And we're going to go through and figure out, okay, what did we just cover and what does some of these big terms mean? And I ask you to kind of be patient, try to keep up with me and try to keep going because we're going to go over this process over and over and over again. We're going to do this a whole bunch of times and we're going to see how this can be used for doing the things that we do as tech artists. All right, I'm going to go over to the lecture and does this work? Yes. Okay, good. Okay, I can't believe it. I just lectured for 20 minutes and I forgot to have the thing, and this was not cool. All right, so what is machine learning? If you look at go into a data model, it's going to tell us it's the data analysis that automates model building. Okay, what the hell does that mean? Okay, that just means is that okay, we had a model. Remember the model that we created? Okay, it was a whole bunch of layers and so forth. And so what does that mean? So what these layers is made up of a whole bunch of things called tensors. Remember that? Tensors? Oh yeah, we remember that. All right, we had a whole bunch of things. And so basically we want to manipulate each of those tensors such that we're going to run through all of the data over and over and again until it actually starts to make sense. And we're going to say, just like your human brain works, we're going to be looking for patterns. And that those patterns are going to be used for testing the truth and anticipating what's going to be next. So as the model gets better and better and better, we're going to start to understand more of these patterns. And then once we understand more of the patterns, we're going to be able to predict what's going to happen next much better. All right, there are two types of machine learning. We're only going to be covering one. The second one is a bit like voodoo, and come to me back in about 5 to 10 years, and I'll be able to tell you more about that. But the first thing we looked at was supervised learning, and that is we're going to have test data, and then for every piece of test data, we're going to have a label. So that means it's going to give us the truth of what we're looking at here. And it kind of looks like this. We started off by acquiring the data, we cleaned the data, and then once we cleaned the data, then we're going to give it an initial testing. And then based on that initial testing, we're going to test, we're going to modify our model. And then we're going to take that model and then we are going to test it again against some data that is a little bit different. And then we realize, oh, okay, the data says that we're not doing such a good job. And then so we're going to take this process over and we're going to train it again and we're going to rebuild it. And we're going to over and over again, we're going to adjust our model so that it starts to work fine. And so we saw that it kind of worked better and better for every epoch that we did. And we're going to do this a bunch of times. 5 epochs, that's not so much. But it may have gotten better as we kept going along here. But once we got done finished testing the model, then we're finally going to say, okay, it's good enough. Then we're going to deploy it. All right, the second type of machine learning is unsupervised learning, and that's working with unlabeled data. And this to me is a little bit like voodoo, but it kind of looks like this. We're going to start off with the data acquisition, then we're going to push that on to we're going to clean it, then we're going to train it and build it. I don't know how, but we do it. And then we're going to transform it into a model that works for us. And then we're going to take that model and then we're going to use it in the real world. Now, come back in 5 to 10 years and I'll be able to explain this a little bit better, but I'm going to focus what on supervised learning looks like. And that all has to do with what we're doing is our perceptron is mimic our neuron. You see this alien creature here? This is what you've got in your head. In fact, you've got billions of them, and they're called neurons. And that each one of these neurons is a cell. And this cell has a bunch of inputs coming in here, and it comes into the to this big central area, and all of okay these inputs are conducting electrical values. So this thing is basically transporting a whole bunch of electricity. Yeah, believe it or not, little bits of electricity are coming through here, and then then this little guy adds up all that electricity condenses all that electricity and passes that electricity down this shaft to this, and then it distributes all the electricity out to all of these little guys. Okay, and that's a neuron. And so what we're going to do as a perceptron is a mathematical model of that neuron. So what does this look like? Okay, it looks like this. All right, so here is our perceptron. And we have a whole bunch of inputs. Each line going into this guy is an input. And for every input, we have the input value, which is the amount of electricity coming in from our prior guy. And then we're going to apply an associated weight to it. And so for every input, it's going to have its own weight. And then we're going to add a bias to it. Now, we're not going to focus on bias too much here, but just know that every input is equivalent to a little bit of electricity coming in from our neighbor, and we're going to weight it a certain amount. And then we're going to take all these values, and then we're just going to add them up. We're going to take all these input electricity, and we're going to multiply each against their associated weight, and we're going to add them all up. This is what that funky signal, the sigma, means, is go ahead and add them all up. Go ahead and add up all these values and pass this along the way. And so that is our perceptron. And remember, one perceptron equals one tensor. We discussed before what a tensor was, and a tensor is basically one unit of AI technology. And that is what a tensor is doing. A tensor is adding up uh, for every input, it has a weight. It is multiplying the weight by whatever comes in, and it adds them all up and passes them along the way. Oh, oh, okay, gotcha. All right, that's fine. I thought I was a little bit confused here, but when we're talking about multi-level neural networks, where it means we're creating a bunch of layers of these perceptrons, and what a neural network means is any more than one layer of neurons. Okay, so the first layer is called the input layer. So we've got these two dots here, and imagine that these two dots are those alien-looking creatures as a perceptron. And so the first layer is called the out, and then we have an output layer going into that. But in between the input and the output layers, they just don't go talking directly to each other. Instead, what we have here is we've got hidden layers in between these two. Any layer between the input layer and the output layer is called a hidden layer. And so in this situation, we have two hidden layers. And that's what we did with our model is we had two hidden layers. And so we said, okay, then they're actually going and talking to each other. And so that's what they're talking to each other is what's called as fully connected. What is fully connected? That means, I'm going to go ahead and show this. That means for every one of these guys, every one of perceptrons we have here, it's going to be passing information to all of the nodes in the next layer. And not just one or two of them, it does it to all of them. And this is what it means to be fully connected. And so that means that we've got this node, it's passing on to all of these nodes, this node passing on all to these nodes. And for every one of these nodes, it's taking that input multiplied by their associated output, and we're passing it on to everyone on these layer. And this one is doing the same thing to whatever gets passed to it, passing it on to here, and then so forth. And then we finally get down to this layer. It's going to take all of its inputs multiplied by their associated output weights, and then we're going to add them all up and then pass them on to each of these output layers. And the thing I wanted to remind you is that a deep learning is a neural network with more than one hidden or middle layer. And we created a deep learning neural network because we had two hidden layers in between in our model. Now, as a reiterator, what did our model look like? We had 784 inputs coming in, and that 784 inputs, remember we had to flatten it out. And so that flatten means was we had to have one big old long list of 784 values for every one of our inputs. And those correspond to 28 rows and 28 columns of pixels associated with what of our images was. And then every one of these values got sent to one of 512 in the one layer size. Now, why did we choose 512? I don't really know. It's just a number that works really well. You might want to try to push that up to 1,000. That would be fine. Or down to 250. I don't know what works better. Go to a more sophisticated AI deep learning course. They might explain where this number comes from. I'm just going to take the number that they gave me and just work with it. So 512 I know works well. And then each one of the outputs for my 512 gets passed on to the next layer. So each one on the next layer receives 512 inputs. And then each one of these 512 inputs sends its output to one of these 10 inputs. Now we said 10. Now we never actually formally defined 10. And I'll show you why we didn't define 10, because we do some kind of special stuff to understand, okay, we've got 10 possible values, 0, 1 through all the way to 9. Okay, so remember that an epoch is all of the training data is run through the model. So if you remember when we ran through, we had 60,000 values. 60,000, that's a lot. But we ran through all 60,000. And so when we go through and we put all 60,000 through, that means that was correspond to one epoch. Okay, and so here's the artist guide to AI. So we're trying to make it a little bit easier. But notice that for every epoch in the training, that there was a loss value. Remember how we came through and we noticed that, okay, we said, okay, here's the loss. Okay, that loss tells us how good the model is. And on every epoch, the weight on each node are adjusted. Remember how each tensor has weights associated for each of its inputs? Well, after each epoch, those weights are adjusted to try to make it better. And then once we go through the whole epoch and the weights are adjusted a million times based on for every one of our inputs, then we're going to run the model again through some test data. And that test data is going to tell us, okay, how good or how bad the loss is. And then we're going to do the whole thing over and over again until we hit done. And so we did it with 5 epochs. And so that means we went through the whole process 5 times. Now, is 5 just seemed to be a place where in general this worked out pretty good. And we ended up with about 70%, which is okay. It's not great. I've seen better, but 70% seems to be okay. Now, remember how I said 30, we said we created a batch number. We said, okay, we had the batch size of about 32 or 36. I can't remember what it was. But instead of using all of the data, instead of waiting until you've done 60,000 values and tested it 60,000 times, it says, okay, we're going to do it in the batch sizes of 32. So what we're going to do is we are going to take 32, we're going to take this 32 times, and then after 32 times, then we're going to adjust all of the weight values. And so this ends up giving us more adjustment time for every one of our epochs. Now, the gradient tells us what the loss is, and it identifies if the loss is increasing or it's decreasing. Does the individual weight increase or decrease? Now, if this sounds a little bit funky, that's because this is a little bit of calculus. This calculus is identified to say, is something increasing or is it decreasing? It doesn't tell if it's big or small, it just says increasing or decreasing, and that's the gradient. And we actually set, okay, what our gradient was going to be. We also set here what a learning rate was. And that means how much or how big do we want the adjustments to the weights to be. Now, the big concern of adjusting these weights, if you set them too big, then it's very possible that you could lose detail or you could overshoot the final result. And if that learning rate or how much you adjust each of the weights is too small, then you might not ever actually get to the answer. If you remember when we were going over the ray marching, the ray would be sent out, and if the ray adjusted too much on it could potentially overshoot the entire volume it was trying to capture. But if we went too short, it might also never get to the actual thing, or it might take forever. And the same thing with the learning rate. And so we have to adjust the learning rate so that it doesn't learn too fast and it doesn't learn too slow. It should learn just right. Okay, the whole process of taking into consideration the gradient and the learning rate and then going backwards and adjusting all of the weights based on that is called gradient descent. And here is a sophisticated solution here where it says a step is updating all of the weights, taking into consideration the gradient and the learning rates. So after every, well, let's see, after every batch, then we took a step. And that means we considered the gradient and the learning rate, and then we adjusted all the weights. And the whole process of doing this over and over again is called gradient descent. Gradient descent, then, therefore, is the process of training a model, taking steps to adjust the weight based on gradient descent and learning rate, gradient and learning rate over multiple epochs. And we do that with the intention of reducing the error as small as possible. And so we want the loss to get small over time. And ideally, it should look something like this. Okay, we started off here and the the error is pretty high and the number of epochs we have is here is with it. But if we keep on adjusting it using a gradient descent, ideally it should get smaller and smaller and smaller until we start to taper off and we just don't get any better. And that is how gradient and learning rate are taken into consideration in order to do gradient descent. But you might be going, okay, we have this green line that's going on here, and this might be the training data. But when we actually try to do it with the test data, remember how we had two different sets? We had the training data and the test data. The test data might actually deviate off here. And so that's why we got to do both in order to consider, okay, are we going in the wrong direction? Because even though our training data might be going in one direction, our test data might not be. And that's a very real dangerous situation. Okay, gradient descent kind of looks like this. Now, if you can imagine, you've got all of these variables coming in here, and not just, and all of these variables are coming in here and they're providing a bunch of weights and so forth. And these variables are changing for every time we run the model. But if the first time that we run the model, we end up somewhere on this chart here, and this is a pretty high, we want to get to where it's actually very low. And so every time we're going to adjust the weights, understanding if the gradient for each of these weights is getting bigger or smaller, then we keep on adjusting them epoch over epoch, and our value or our loss keeps getting changing over time. So ideally, it changes so that this value starts getting smaller and smaller and smaller until you get to a situation where it actually gets into the lowest point possible. And when you get to the lowest point possible, that means is that you're honing in on the solution. This is the process of called gradient descent, because if you notice here, this is kind of like, I was told that this is the path that water naturally follows. If you go ahead and drop this, then the water technically is going to follow the path of gradient descent and the path of where the water follows mostly in this. And the same thing applies to our data. Okay, an optimizer is a algorithm that adjusts our gradient descent over time. And so it's a strategy for providing the least amount of goof up because it's a mathematical model. It's not going to be perfect. And Atom is the optimizer that we used. And there are other optimizers that we could use. And one of those could be called RMS prop. and that is currently a very hot technique into the realm. Now, the thing that we got to remember here is that for every tensor that we have here is we have a activation function, because we're not just going to add all of the values in our tensor. We're going to add the weights modified by their inputs, and we're going to add them up, all those to this. We're going to have our weights and inputs added up all together. So if we were to just take whatever input we have and then output that along our way, then we'd end up with something called a linear activation function. Remember, we had a whole bunch of linear stuff on here. We said uh, we want a bunch of linear layers to go through. Well, this is what the linear meant, and it means it was an activation function. And so it's kind of like saying, okay, the values in kind of like go linearly along the way out. And so we have a nice progression on the way out, so it's nice and linear. And so it kind of looks like this. So our output is kind of like looking like this as we're going along. And that is what it's meant to be linear. Now, we have an activation called a ReLU, which means, okay, this is very fancy here. That means we're going to output 0. We have no value until it is greater than, we're going to have a value of, until we have a value greater than 0. And so that means that the output here is going to, until we reach a total sum greater than some kind of threshold value. But once we hit this threshold value, then we're going to push forward to be whatever our sum actually is. And this is what's called ReLU, and I forgot what ReLU is, kind of like rectified linear units and so forth, and because it's going to be 0 up until it reaches some threshold, and then it's going to pass on the sum of whatever's coming through. And so mathematically, for those of you with a mathematical background, it looks something like all of this. Now, there are other functions that we might want to take into consideration, and one of a possible one is called sigmoid. And look at this crazy ass function here. Believe it or not, you've seen this function before, and if it remembers it, it's Gaussian. Remember what we are doing with the motion blur or the screen space when we were multiplying in convolutions? We use this function in order to guesstimate how much percentage or how much weight we wanted the environments to do. And this is called the Gaussian function. And this is what it looks like here. And it means is that the values here are going to start to be small, and we're going to keep them small until we reach a certain point. And at this place where we want it to get bigger to around this point where it's going to be increasing the fastest. And then we're going to want things to slow down. We didn't use any sigmoid functions for our tensors on the last one, and I don't know if we're going to be actually using it, but I just wanted you to be aware that there's actually a whole bunch of different activation functions, and they all have their various purposes. And so we go. There we go. There's our sigmoid function. Okay, now at the very end, we didn't actually put down, create a final layer that is 10 objects wide. Okay, instead what we did was we used an activation function called softmax. Now, if you remember softmax, this means is that it adds all of the sigmoid results and it reweights them to add up to 100%. And so that means is that when we use softmax, it means, okay, we told it to be 10 units wide. So what it's going to do is it's going to add a weight to every one of these output values, of which we said we wanted 10, and then the sum of all these is going to equal 1. Now, ours didn't add up to 1. It added to like, one was like 25, and one was 2, and one was like 14, and you could get a whole bunch of wild, crazy stuff depending on what functions that you use. But in this situation, If you look here at 0, 1, 2, 3, 4, 5, we identified 5 as to be the correct value. And on this test run, it says, oh, it's a 0.9, which was much better than ours when we said it was going to be about um, a little over 50%. So this one, this represents it. Okay, so this is called one-hot encoding. I don't know why they call it that way. The name is actually a lot sexier than what the reality is, in my opinion. But I don't think there's anything really hot about this data. But that's what it means, is to take all of the middle class, the middle layers, and then bake them down into just a fine set of outputs, and that's called one-hot encoding. All right, now we dealt with something called cross entropy, and this picture says, oh, it says cross entropy is nearly explained. So we've got this path that is ideal. And the cross entropy tells us how good our model is working. And so it tells us it's an additional step to tell us how good or how bad it is working. And this value is used in consideration when we're using our gradient descent. And so this is the path that we essentially want to take, and this is called cross entropy. All right. So what we're going to do is we're going to create the MNIST again, but instead of the numbers that we used before, we're going to use the American Sign Language. And that is, we're going to use little pictures with people moving their hands. And so what we're going to do is we're going to have to download the ASL data onto our machines. If you remember last time, we used the data that was that was given to us from the torch information, and we had to download all that. But most probably torch won't have data for us, so we have to use our own data. So in this case, I came up with our own data, and this is the American Sign Language. And so if you go into your if you go into Canvas, then we're going to find out the data that we're going to need. All right, so I'm going to show you where to download that from. All right, tech artists, we are going to download our own data, and that data has already been prepared for you, at least partially. So if you go over into Canvas, come on over here to Files. You should see on the miscellaneous, click on miscellaneous, and there is a file called aslData.zip. Go ahead and click that, and go ahead and click on download, and that will download onto your machine. So once it finishes downloading, so what we're going to do is we're going to go, oh, okay, okay, so we want this. I'm going to go ahead and grab my file browser. Okay, where's my browser? Oh, here it is. Yep. Okay, there it is. And we said, okay, there's my data. There, looking for my downloads. I'm going to go ahead and I'm going to copy this data, and then I'm going to go and paste this over into my TA20 demo. Now notice that the TA demo should have the Jupyter Lab test that we put in there, and there's our last MNIST, but it also has a data folder. Go ahead and double click and go into the data folder, and then paste your ASL data right in there, and then right click on that and say extract all. I'm going to click extract, and then it's going to load a bunch of stuff, and it says, ooh, we got a bunch of stuff on here. What's in here? I'm going to drop in here, and inside of the ASL data is that with it. We're going to have a bunch of images, and then we're going to have this sign mnist.test CSV and sign mnist train CSV. So these are going to be CSV files that contain all of the information we have here, and it's duplicated here into this test folder and to this training folder. So it kind of like positions both purposes and so forth. So we've got that downloaded into our project, and so now we're going to go in and modify our project and create a new MNIST based on the data that we just downloaded here. All right, so I'm going to go first and I'm going to create a brand new notebook. I'm going to click on here, notebook, and I'm going to call this rename, and I'm going to call this MNIST underscore ASL. All right. Okay, so we're going to go through here and then we're going to import all of the stuff that we imported last time. And it's going to look something like this. We're going to import torch NN as NN. And we're going to import pandas. Now, we didn't use pandas before, but pandas is going to be used as a way of organizing our data. Pandas is a little bit like NumPy. We're going to import the torch, we're going to import our optimization, our atom function, and then we're going to import data sets and data loaders. And I'm going to also, we're going to test to see what our device is. Now, I realized I had a more complicated and sophisticated device that took under consideration other parameters, but really all we need to do is test to see if we need a CPU or a GPU. And so here is a kind of condensed version of that. We're going to say device equals the torch device. Make it equal to CUDA if CUDA is available. Otherwise, make it the CPU. And so we're going to load this in, and then we're going to test and set our device. And I'm going to execute this, and it's going to plug and chug and cook, and it's going to say false. Okay, so it says false, so we know that device is going to be equal to our CPU. Now what we're going to do is we're going to read in our data. And then so we're going to be reading it as CSV files. Now, a CSV file is like an Excel, but it is done in as a text file. And this text file has just data on here. And so we're going to click this in here. Oops, that's not what I wanted. I'm going to go forth to here. And we're going to read in this data. And we're going to read it in as two parts. We're going to import it as the training data and as the test data. And so here, we notice that we have, here's our data folder. And then so we're going to go data, ASL data, and then sign MNIST train CSV and so forth. And we're going to read this into there. This is what we're going to use pandas for, because we wouldn't be able to use the other libraries to read from a CSV file. That's what we're going to be using pandas for. And so we're going to go ahead and execute this. Okay, so what does this actually look like? It might look just like a bunch of gobbledygook. So we're going to explore what this data actually might actually look like. And then so I'm going to, I said the train.df, and it's got a little function called head. That means don't give me all 60,000 values. Just give me the, just give me the head, the first 5 values. So, all right. So we said, okay, we have the label. Okay, this is a 3, 6, 2, 2, 13. And we're probably going, oh, that's kind of strange. In the American Sign Language, aren't there like 26 values and 26 shapes? Well, that's exactly what they're doing. They say, okay, the first one is label 3. Let's say that would be A, B, C, D. Okay, the first one is a D, E, F, G, and the second one is a B, or a C. This is a C, this is a C, and this is the 13th value, which I can't remember what it is. Okay, but notice here that we have the pixels associated with this, and this should have 784 pixels. And you notice that they are presented as from values from 0 to 255. And so those are the intensities of them. Okay, and so here we have as our data. Now this is the kind of data that you're typically going to get. And so we need to learn how to kind of condition and train all these. But notice here that the label here is put in right in every single entry, let along here with all the pixel data. So the first thing we have to do is extract and separate the training values from the other data. So we're going to use pandas yet once again in order to help extract that data. Oops, look at that. We don't want this. And we don't want that. You have to remember that. Okay, so here it is. For every single value on here, we're going to be popping off the label, which is the first column. And then we're going to be passing those values off onto the X train and the Y train and the Y valid variables. So we're going to be removing or extracting the labels and then moving the labels to new variables. So we're going to have what's left over and so forth. And so I'm going to take a look at what the Y train is going to look like. So say Y train. What is the Y train going to look like after we do all this? Okay, and it says, okay, the Y values are 0, 1, 2, and those are 3, 6, 2, 2, 2. And then we're going to go all the way down to, okay, there's 27,000 values here. Almost 27.5 thousand values here. And so these are all the labels coming out of here. Now, we still have to kind of extract the actual images we want out of here. So we're going to extract the images now by using something similar what's left over. Remember, we popped off the labels. And so let's extract the images. And so we have X train and X value. And so we're just going to take whatever the values is left over. And so let's take a look at what the X train looks like. And we're going to execute this. And we say like, okay, it's an array. It's in a whole bunch of information. So each row here constitutes as, what is that, 784 values. And then we have 27,454 rows of 784. Ugh. Okay, so that is crazy. So let's take a look and see what these actually look like. And Pandas has a little function here called shape that will tell us what things are looking for. Oops, I don't want this. Okay, so what is the shape of this data here? What are we actually looking at? Okay, we're looking at almost 27,500 lines of 784 values. And if we do the same thing for the Y train, so we go Y train dot shape. What is that? Okay, there's 27,500 values of just one. Okay, so then we know what it is. And so how many do we have for the valid? So if we type in X valid dot shape, and we'll put Y underscore valid dot shape so we can get both values. Oops, Y valid. Okay, so it doesn't want me doing two at once. Maybe if I put a comma there, it'll allow me to do it. Yeah, there it is. Okay, so our training data doesn't have 10,000 values. It's got a little over 7,000 values. So that means our our test data set is about 7,000. Okay, so we know that this all works. So let's go ahead and start building this. So let's take a look at one of these things. What do they actually look like? So we're going to use the matplotlib in order to visualize one of these things. Now, mind you, this is still just the raw data. We have not actually converted it yet. So we're going to use the matplotlib, and we're going to take the plot figure, and we say that it's 40 by 40 to make it look like a side, but we want to actually take a look at what one of these things actually looks like. Okay, so we're going to plot the figure, and it says 0 is 4,000 by 4,000, and okay. So that doesn't give us too much information. So what do we need to do this? We need to actually show a whole bunch more. So I'm going to take over 20 values. Oh, that'll probably look good. and so forth. So I'm going to run another function on here in order to just manipulate and all this. And we're going to say, okay, what we're going to do is have 20 images. And for every one of these images, then we're going to take the row is going to be what the x-train value is, and we're going to call it I. So we're going to take the ith value, and there's our label, and then our row dot shape is 28 by 28. Okay, so we know what the row is. We have our image, and then we're going to make a subplot and a title and an axis and an IMG show. Okay, this is not really. This is more just understanding how pandas works and how pandas can be used to help visualize and organize our data. This isn't really part of the deep learning process, but it's just to familiarize, how you could use these tools in order to make things better. And I'm going to go ahead and change this, to where it should be. And so we enter this. Oh, look at that. It overlapped them and it did each other. So this looks, it's a little bit to that. And I don't know how to spread them out so that it looks a little bit better. So I'm going to re-execute this to make it only 10, and maybe that will make it look better. Okay, so there it shows what some of these things look like. We've got 3, 6, 2, 2, 13. So if you understood sign language, you would understand what all of these means. Okay, now remember how each of these values is somewhere, for our pixels, the pixel values are between 0 and 255. Well, we have to change those between 0 and 1, and that's called normalizing the data. So let's go ahead and normalize this data. And all we're going to do is take these values and then divide them through by 255. And, okay, so if we do that, okay, well, what does it look like? So if we take a look at X-train again, we notice that it's the same thing as what was presented before, but now those values, they're no longer integers between 0 and 255. They are now values in between 0 and 1. So they've been normalized and they are now ready to go. All right. Now, before we used a data set that was given to us, and we just kind of took it as is. Now, normally what we have to do in order to do a data set, we want to create a custom data set. And so what we're going to do next is going to create a custom data set that is working on it. And in order to create a custom data set, it has to have, it's going to be a custom class, and it's got to have 3 different functions. It's got to have its constructor, it's got to have a get item. That means that when we do an index on it, it returns which value, and it got to be able to return the length. And so these are the minimal 3 functions or methods that each class has to have. So here's our data set. And you'll notice that we're going to create a new data set called my data set, and it's going to use from the parent data set class that we imported right up there. And so here's our constructor, and we're going to get a x data a data value, a data file, and we have a y data file, and then we're going to create a self xs, and which is going to convert all of them to tensors, and we're telling it to transform it right here. Transform each value to a tensor that is a float and it's adjusted to our device. And here we're going to do the same thing to a y. We're going to convert it to a tensor. And when we're going to say get item, that's a overloaded function that's going to return either the xs or the xs and the ys values according to whatever index is given to us. And if we wanted to do the length override, instead of giving us the length of the entire data set, it's going to give us the length of whatever xs is. And we could have done the same thing for x, y, but we're just going to leave it as is. Okay, now we're going to get back to doing the things that we had seen before. All right. Okay, we're going to find the batch size is 32. That means that we're going to iterate through 32 bits of data every time that we go through, and it's going to look at 32 sets, and then based on the value, it's going to create it's going to go through, use gradient descent, and update all of the float values. And so here we go, we're going to create our trained data set, and we're going to first create a data set out of it, and this is from our custom data set. And then once we have our data set, then we're going to use that in order to create our train loader. And now the train loader is what PyTorch likes to work and use with. And so data loaders are cool. The difference between a data set and a data loader is a data loader is iterable. It means it iterates very well, but you can't use an index. A data set, you can use an index, and that's why we have both values, a data loader and a data set. It's a little bit nutty, but this is the way they do it. But we said, okay, here's our training data, and here's our batch size, and then we want to shuffle them. And then we're going to keep track of what our length is. So here it is. We're going to take the length of our train loader of our data set here, and that's going to be assigned to train n. And while we're at it, let's go ahead and do the same thing for our validation data. So they're really just kind of the same thing. And then we're going to create a data set, and that's going to go to valid data, and then we're going to create a loader from it, and then we're going to grab our length. All right, not too much going on here. And so to see what each of these loaders look like, let's see what, let's create a certain batch here. And we're going to go here and let's take a look out of here. All right, we're going to say, okay, we're going to try to iterate through this train loader. Remember what I said, the data loader, it iterates, so you can't look at anything. So we're one by one, we're going to load into here, and we're going to try to get to take a look at this. And it says, oh, batch is not ordered. Okay, I named this wrong. This should be train loader batch. Now if we execute this, okay, there's the values. And so there's the tensors for the train, the data. Here's the image, and there are the associated, there are the associated results. Okay, now if we did this for the entire data set here, now if we were to do this again, we're going to iterate through. So that's what next in the iter does, is this is iterating through this. If we do this again, we can get different values, and it's going on, on over here. Yep, see, every time we execute this, these values start changing over and over and over again. And so that means is we're going through every single episode of the loader, and we're accessing things over and over again. So let's take a look at the image and the shape. So if we, okay, now notice that there should be 26, should be 32 values here, because 32 values corresponds to one batch. So this is 32 values. And so if we say batch, and we're going to go train loader batch, 0 shape, and then let's hold off on this and take a look at this. Okay, and so this is the size of it. It's 32 values. So this is correspond to the batch size of 784 shapes. Now, if we were to take a look at what our labels look like. Oh, hold on. All right, I want to test to see what the shape of my labels are. So I'm going to go ahead and where it says train loader batch, I'm going to change this index from index to 1, and we'll take a look at that. And it's going to be 32 sizes too. So it's all about 32 size. And so that's what kind of like what we're looking for. All right, now we've got that done. So let's go ahead and start building this model. And so we know that the model that we have here is going to be about 28 by 28. So we're going to say that the input size is 28 by 28. And so ultimately, we know it's going to be just one color. So we can say 1 times 28 by 28. And so that was good. And the number of output classes is 26. All right, that's fine. So let's go ahead and create our model. We can keep this nice and simple. And we've got that. And so here we have is our sequential statement. Our model equals nn.sequential. We're first going to flatten the data. We're going to convert it from being two-dimensional objects into just one flat, one row of 784 float values. And then we're going to put this through a linear activation to it. And we want the input size to be 784, and we're going to output it to 512. And then we're going to pass them on to ReLose. Then we're going to go on to another line, or we're going to call these linear, 512, and we'll pass them to another set of linears. And then finally, we're going to go into one final set of linear things. And the input size of each is going to be 512, and it's going to go out to the n number of classes, which is 26. All right, and so here is going to be our sequential model. And let's go ahead and build the model here. So I'm going to say model equals torch compile, and we're going to compile it to whatever the device is. And then while we're at it, I'm going to set my loss function and my optimizer to be exactly what we created before. So I'm just going to copy the data from our old project and then push that along here. And I want to take a look at what our final model is. So I'm going to just pop that in here and take a look at our final model. And there it is. And this should be exactly what our model looked like before. If we compare this right here to our model, well, right here, it's basically the same thing. It's that it doesn't have the final linear thing for our output. And then we just added our final output here. So we're going to handle our training functions just a little bit, our training and our test functions just a little bit. And so we're not going to do the softmax in here. We're going to let this be handled right into this final layer. So let's go ahead and modify our training function, which is going to be almost the exact same function that we created before. And so we're going to set our loss and our accuracy to 0. We're going to train our model, and then we're going to iterate through our loader. Remember, loaders are good for iteration. And then we're going to test out our data. We're going to modify our optimizer. We're going to modify our batch loss, and we're going to use backward propagation, and we're going to use the optimizer, which is the atom optimizer, to optimize this thing. And we're going to go to our batch loss, and we're going to pass this off, and this is going to go on, and we're going to take a look at our train and accuracy. And there's our train n. Okay, so let's take a look at our, and oh, I don't want it to confuse you folks. And so we might want to put just loss right in here and put accuracy right in here. And we're going to get rid of this. And then we're going to put an F right here. And so things are going to look a little bit more to what you're used to. We're going to hit execute that. So here's our training function. And we're going to create a validation function. And this is the validation function. It's going to look exactly, almost exactly like what we were looking at before. Here we're going to start initialize our loss and our accuracy. We're going to set our model to evaluation because we're no longer training it. And then we're going to go through torch no gradient. And then we're going to go through each of our valid data, go chunk, chunk, chunk all the way through. And we're going to calculate our loss and our accuracy. And then we're just going to sum them together. So this is really no different than what we were looking at before. And so our train function and our validate function is exactly the same what we've done before. No need to type those in again. And I'm just going to change this to be something a little bit more modern, a little bit more Python 3 instead of Python 2.7. All right, so let's go ahead now and define our accuracy function. This is the exact same function that we created before, so I'm going to copy this from my old project and put that right in here. So there's our accuracy function. It's the exact same thing. And then for the more or less, we're going to start training this along the exact same way. And we say epics equal 20. Yeah, this is because our data set is going to be a little bit bigger. It's no longer 10 values, it's going to be 26 values. And so we need to consider what these values are going to a little bit. So we're going to go ahead and execute this and let it rip. Okay, gang, we finished processing, we finished building our model. And if we take a look at the process that we started off at, an accuracy of around 50%. That's not so good, but as we kept on going iteration over, we finally started increasing our accuracy more and more and more. Now notice that during the training, our accuracy starts to get very, very good. Because that's because there's kind of familiarity that goes on with the data. And that's why we don't use our data to actually test the model. We have to use our validation model. And we start, I think the highest we got was about it's closer to about 80%. While the training is supposed to, is near perfect, the validation is lost. So we still ended up around 80%. Now, we have to concern of ourselves about that, and we can do better. And the next lecture that we'll go on to next week is we're going to go on and we're going to see like, okay, how can we actually make this better? And we're going to validate this and we'll say, okay, let's use convolution neural net. Well, let's use CNNs. Well, let's use convolution filters on this. And if you remember, uh, when we use a convolution matrix, we can identify edge detection on here. And we looked at this a little bit last semester, and we're going to return back to that. We're going to use the exact same algorithm in order to use edge detection in order to understand, okay, are we looking at the shapes in order to help us to identify these things? Okay, thank you very much for your attention. Thank you very much for your patience. And I look forward to presenting the next phase along this journey of deep learning madness. All right. Until next time, arrivederci.